So first of all, let me go through questions people had about the assignment. I'll start with 5 and 6. Anybody have the homework? Out? Okay. So problems number 5 first. Okay, so in a heat engine, a heat source increases the temperature of the gas, and the gas does work as it expands. Well, to be more explicit, I could have said that the system, your chosen system, is the gas. That's what it's always going to be in engines and refrigeration systems. So a heat source increases the temperature of the gas. And then this increase in gas temperature, the gas wants to expand, and that expansion of the gas does work. On the surroundings. So what are the signs of Q and W? Mm-hmm. That's right. I was wondering if you could explain more as to why. Yeah, okay, so Q is positive if energy is added to the system. Yeah, through heat. If energy. So I'm trying to word this in a specific way because heat is not a property. So people talk about it kind of as if it is, just because the wording is so awkward to be technically accurate about it. But you never add heat. Okay, heat represents a process. You can only add to properties or subtract from properties. You know what I mean? So when there's heat transfer, one thing gains energy through heat and the other thing loses energy through heat. And I'm sure that there are going to be times when we're going to be sort of loose in the way we talk about it because that's just such a mouthful to say. But keep in mind that it's energy that's changing hands. Heat is not a property, so you can't increase the heat in something. You know what I mean? It's a process that changes energy. It's energy that's right. So Q is positive if energy in the system increases due to heat. And W is positive if energy in the system decreases due to work. So that's what, when I was saying the thing about, in a heat engine, Q and W are positive. It's because this sign convention, you can think of it as, I don't know if this is really where it came from, but I wouldn't be surprised if it was. The sign convention you can think of as being defined by what happens in a heat engine, you know. That's where it comes from. Yeah, in a gas, that's right. So usually we're going to calculate that as PDV, the integral of PDV. So if your gas gains energy through heat and loses energy through work, through doing work on the surroundings, then Q is positive and W is positive. So now let's think about, so this is exactly what happens in a heat engine. By the way, Thursday is the first quiz. So the last 15 minutes of class, we'll do a quiz. And the quiz is going to be mostly short answer questions about stuff I've said in class. There'll probably be one homework question that you'll have to recreate, or part of a homework question. And there's almost certainly going to be at least one question about this sign convention. Okay, so this is an important thing to be clear on. Okay, so number 6. In heat pumps and refrigeration systems, a gas is compressed to raise its temperature. Remember, if a gas is insulated, so it can't exchange energy through heat with its surroundings, and you compress it, the temperature of the gas is going to go up. So the gas is compressed to raise the temperature. And then I guess what it doesn't say here is then that higher temperature gas loses energy to the surroundings through heat. And just intuitively, we're going to talk a lot about heat pumps and refrigeration systems. So how does this work the same for both of them? So the idea is that in a heat pump, you compress the gas, with some kind of motor, you compress the gas. Now it has a higher temperature, and now you put the gas into a region that can exchange energy through heat with the room that you're trying to warm up, and it heats up the room, and then you put it back through the cycle. In a refrigeration system, the way it works is you compress it, the temperature increases, then you run it through the coils in the back of the air conditioner. That allows energy to leave what's now a high temperature gas into the air outside the house. But now your gas has less internal energy. Now you let it expand again, and it's cooler than it was before. And then you let that exchange with the room. And now the room is adding energy to the gas, which cools down the room. So really it's the same system. It's just a matter of in the two exchange regions where you're exchanging with the room that you care about and where you're just rejecting it somewhere you don't care about. Okay, compressed raise the temperature. Then that higher temperature loses energy to the surroundings through heat. Okay, so what happens here? So the gas is compressed. So is work being done on the gas, or is the gas doing work on the surroundings? On the gas, and so is that positive or negative W? That's negative. And then the heat happens in those exchange regions. Is energy being added to the gas at that exchange region or removed? So heat is leaving the gas into the surroundings, and so is Q positive or negative? Negative. Any questions about those two? So yeah, that sign convention, I mean, if you can keep that sign convention straight in your head, that's going to carry you a surprising way through this class. And if you understand everything else I say and don't solidify that sign convention, you're going to get problems wrong all the time from that the whole way through the semester. Okay.
I don't really know how to phrase this question, but it seems the reason the Q being negative is counterintuitive is that in short term the temperature increases, I guess.
Okay. Yes. Yes. Okay. Yes. So I think the tricky thing with that is that the way we use the word heat in everyday language is different than what it means in thermodynamics or in physics. So we say heat to mean an increase in temperature. And so that's where the confusion is. But that's not what it means. Heat means specifically this: a change in energy to the system due to a difference in temperatures. Okay, and so if you're compressing this gas, you're raising its temperature, but it's not coming from any difference in temperatures. Yeah. It's coming from doing work on it. Okay. Not work. You put your warm face right in front of those coils, and that's creating a bigger temperature difference between the gas inside and the surroundings, and so you're aiding heat. You're aiding the exchange of energy through heat. But to do work with your face, you'd have to press your face really hard against the coils.
But so Q is negative for your face.
So if the system is your face, which it never will be in those, then yes, your face is emitting energy through heat, and so Q is negative. Q face is negative. That's correct. Mm-hmm. Your signs would then flip on the W, right? No, the equation is still the same. You know, it's like the equation is this, no matter what. So the change in energy is equal to Q minus W. But now if Q is negative 400 and W is negative 850, then that says that the change in energy is equal to negative 400 minus negative 850. You know, the equation's still good. You just plug in the negative numbers. Okay. Any other questions about that? Yeah. Okay. So number 4 is related to numbers 2 and 3. So let's think about those for a second. So number 2, so does a gravitational force higher or lower gravitational potential energy? So gravity, no matter where you are, it's always pointing down, right? These are the, if that's a force field, that's the direction of the force at each point. Where is gravity? So it's pointing down. Does potential energy due to gravity get higher as you get higher or get higher as you get lower? Yeah, the potential energy function is mgh. So gravitational potential energy gets bigger as h gets bigger. And so this is high potential energy, this is low potential energy. And so the force points in the direction of decreasing potential energy. If something starts fast and the only force acting on it is gravitation, gravitational force is going to decrease its potential energy. Okay. So number 3 now, let's think about spring potential energy. Okay, so here is the starting point. Okay. And oops, the spring's connected to the wall over here. Okay, so what happens if you move the object this way, stretch the spring? Yeah, it wants to, so that force is going to pull it back towards this resting length of the spring. And what happens if instead of stretching the spring, you started here and compressed it? What direction would the force be? Back towards resting. And so the force is always pushing back towards the resting length of the spring, where the object is at the spring's resting length. So where is, so the force is this way here. If you compare the green and the red, which of those has higher potential energy? Green has a high potential energy. The resting point has a low potential energy. And so that force always points toward decreasing potential energy. If you start an object that's connected to a spring, if you start it at rest, that force is always going to be moving it back towards zero potential energy, and it's gonna, in this case, it's just gonna oscillate back and forth if there's no other forces. But that in every instant, that spring is trying to push it back towards here. The spring, what the force it's applying, is always trying to get it back to rest. Okay, so number 4 then. The idea is that's what a potential a force field always does, a potential energy field. A force field always acts toward lower potential energy. And that's true in, in circuits or electricity and magnetism, where you talk about electric fields, and electric fields are related to electric potential, which is related to electric potential energy. Those electric forces are always trying to push charged particles towards a lower electric potential energy. That's just a property of potential energy fields. Any questions about that? I want to say one thing, or ask one thing. So when I was talking about potential energy, I was really emphasizing the fact that potential energy is just, like, really the way to think of potential energy is as an easy way to do work for conservative forces. And so, work is not property. It represents a process. Potential energy is defined to make work calculations easier. And so, what about potential energy? Does that have to do with a process, or is that a property? Well, potential energy is still a property. Like any type of energy. Work is negative change in potential energy. And it's that change in potential energy represents a process. But, change in potential energy is just the potential energy at some later instant minus the potential energy at some earlier instant. And each of those individual potential energies represent a state, and those are properties. Okay? So it's like internal energy, kinetic energy, potential energy is a property. But it's a property that makes it really easy to calculate the work done over a process. Any other homework questions? Okay. So we were in the middle of talking about radiation last time. We were talking about the three the three ways that heat can, the transfer energy through heat can occur. We talked about convection. We're in the middle of talking about radiation. And then we're going to talk about convection. And I said that Q dot subscript E is equal to Greek letter epsilon times sigma times A times T to the fourth. This is the rate of heat. This is the emissivity. This is Boltzmann's constant. That's a universal constant. And then A is the surface area that's exchanging heat. And then this is the temperature in some absolute scale. And keep in mind that this is the heat that's the energy that's emitted. This is energy removed from the chosen body. Removed from that body, and then so whatever you have as your specified system, you need to use this fact to figure out what the sign is. So base the sign on that. One case that comes up pretty often is that you have a smaller body completely surrounded by a much bigger body. I said that a body is always emitting radiation, but it also is always absorbing radiation and transmitting radiation and reflecting it. And so the amount of energy that's being radiated by a body is only part of the story. But in this one case, if you have a smaller body that's completely surrounded by a bigger body, we can actually calculate the net rate of radiation. So only then can we calculate the net radiation. And that follows the formula QE dot. So the rate of net radiation is equal to the emissivity times Boltzmann's constant times the area that's surrounded by the bigger body. times the quantity temperature of the body to the fourth minus the temperature of the surroundings to the fourth. So TB is the temperature of the smaller body. The B on there is for the body. And TS is for the surroundings. So TS is the temperature of the larger surroundings. Okay, so this says it's the net rate of radiation emitted. Look at that formula and tell me if that's the net radiation emitted by the body or by the surroundings. And how can you tell that?
Because it's a positive quantity.
Yeah, very good. Yeah. So you know that the higher temperature body is going to a higher temperature body is going to have a net emission of energy, and so you can see that this is only positive if the temperature of the body is bigger than the temperature of the surroundings. So this is the net energy emission from the body due to radiation from the body. And then the last way that energy is transferred through heat is convection. And convection depends on a lot of stuff. So convection is heat. Yes. Mm-hmm. Yeah. Yeah, I don't know how this is derived, but yeah, something about the fact that this is the only place where I think the energy can only end up in two spots. It can end up in the body or it can end up in the surroundings, you know. So if it's not totally enclosed, and I don't know why I also don't know why the surroundings have to be much bigger. I don't know. I've never seen the derivation, but definitely if it's not surrounding it, you can imagine why this wouldn't work because, you know, some energy could go to that chair or whatever, some doesn't have to, and it's very case dependent. Um, any other questions about radiation? Okay, convection, heat. I don't know how I was going to word this. Heat occurs through let's say the macroscopic motion of energetic material properties. In other words, the actual surrounding material properties, material particles, sorry, move away from the chosen body. So like an example is if you have a high temperature object surrounded by water, and you make the water flow over the object. Conduction is always happening from the object to the immediately surrounding, water in this case. But then you'd have this buffer surrounding the object that would make future conduction happen less. If those high temperature water particles stayed right around this rock or whatever it is, remember that conduction depends on the temperature difference, right? So if this water here gets to be a higher temperature, that temperature difference is reduced, and future heat loss through conduction is going to be smaller. But if this heats up the surrounding particles, and then a flow of the water carries those away, and then those are replaced by cold water surrounding the rock, then heat is going to happen faster. If you've ever, anybody here ever had an ice bath? That's how I know about convection. Like if you, like when you should have tried it last week.
I did it.
Yeah.
One of the obstacles.
Oh, really? But so like when you have injuries, when I was much smaller, I used to be a distance runner, like in high school and stuff. And when you have injuries, like you ice it, and you can get really effective icing of a lot of muscles by just dunking your foot in this super cold water, And so you dunk it in, and it feels horrible, and it's just aching. It's just horrible. You're like biting stuff to keep your leg in there. But then you feel like you're getting used to it, And you're like, oh, this isn't so bad, And then the trainer comes in and swirls the water around, and you're like, oh my God, yes, it's horrible. Because like your leg heats up all the water right around it, and if it stays still, you don't have any convection effect. The convection happens, and it's horrible again. Okay, so this is a hard thing to quantify because there's so many things that go into it. The shape of the material, the flow pattern around it. Like you can imagine, it's this crazy thing. And so what we do to calculate heat convection, energy loss through convection, is we basically have like a constant that lumps all that stuff in together. And if you happen to have done experiments to find that constant for your particular application, then you have this simple equation you can use, So the equation, you will see that I will give it to you, says the rate of energy loss through heat is equal to a constant H times A times the quantity of body minus temperature of the TA. That's the surroundings. I don't know why that's called A, but we'll call it that. Okay, so this is the rate of energy transfer. H is a constant. That takes into account the relative conductions of the two materials. It takes into account the flow pattern, the surface shape, And that's all I can think of right now. There might be some other stuff, but even just that's a lot of, like, there's no reason to think of this constant as some sort of fundamental property of a material. But if you do an experiment to try to fit this, uh, for your specific thing, try to fit this equation to the heat loss you have, and you can use that in future. Yep.
So you would have some shape that you want to know is constant, or you would do tests.
And for a certain pattern of flow around it, yes.
Right. So
that's right.
If you scale that up and everything scales identically, does the constant also scale directly?
That's the idea.
Okay.
Yeah.
So this is kind of analogous to the drag.
Yeah. Yeah, I guess you could say that. Although you use the drag coefficient, at least that equation has more to it than this one, but yes, it's sort of the same idea, right? But anyways, you see that this A is the surface area exposed to the flow. TB is the absolute temperature of the body. Well, this is a difference, so it doesn't really have to be absolute, I guess. Is the temperature of the body. TA is the temperature of the fluid. And notice that, again, this gives the rate of energy leaving the body. And so remember that with all these equations for these heat processes, the sign convention that's given in that governing equation is not necessarily compatible with your sign convention for the energy equations. Okay, so you have to take these magnitudes and then think, is my system gaining or losing energy because of it? Yes. That's right. Exactly. Yep. And then after you've figured that out, you need to think about how that relates to your system, whether heat's going into your system or leaving your system. One thing, so notice that all of these, for conduction, radiation, and convection, heat is represented as a rate. You can use this in the first law of thermodynamics. If you take the time derivative of the first law, take the time derivative of every term in the first law, And that gives you the differential form of the first law of thermodynamics. And it looks like this. So we have ddt of the total energy of the system is equal to Q dot minus W dot. And the EDT, you can break that up into the time derivative of the kinetic energy plus the time derivative of the potential energy plus the time derivative of the internal energy. And this is always given with energy written with the ddt notation. And the time derivatives of Q and W as given with that dot notation. And it's sort of a funny notation. It's really just sort of a reminder. The dot means ddt, so that doesn't change anything. But it's a reminder that this is a property, okay? So if you take the time derivative of a property of the energy or the time derivatives of any of these properties, it tells you how much those are changing over time. These are not properties. And so if you take the time derivative of Q and W, it tells you the rate at which, the net rate at which energy is changing due to work and heat. Okay. They mean different things.
Okay, I feel kind of dumb for asking this, but what is capital U in this case?
Internal energy. And like I've said before, you can always think of this two ways. You can think of the potential energy as being part of the total energy, and then your work term only deals with work done by non-conservative forces. Or you can think of your difference in potential energy as being the work done by the conservative forces, and then don't put it in there. Okay. It's the same thing either way, but you have that choice about how to think of it, sort of. So this differential form of the first law of thermodynamics is something that you can use instant to instant. It has to hold at a single instant. Notice that our other way of representing the first law of thermodynamics was all extensive properties, and so that you use over some interval of time. Okay, but this is an instantaneous equation. So this holds at each instant. And you can use this For steady state processes, and that's one where no properties change. Or for transient processes, where at least one property is a function of time. So let's see how it works in both of these two cases. So here's an example of a steady state process. So let's say we have a gearbox. Here's the boundary of the gearbox. Question? Anyone? Do you have a question? Okay, so you have a gear connected to this shaft that's bringing power in as an input. And then that's connected to, that articulates with this other gear. I just drew them as wheels, but the idea is that those are connected. Those are two different gears. And the input to this gearbox is work done on this shaft that's equal to, we'll call that W1. And the output is, so if this one is turning this way, down to the bottom, this top gear is pushing out. So that means the top of this gear is pushing out, which means it switches the direction. And so the output is work done in the surroundings over here in the other direction. I'll call that W2. And the outer surface has an area of 1 meter squared, total surface area of 1 meter squared. And it's cooled through convection. So the outside of the box is cooled through convection with the convection constant of 0.171. The units you can figure out from the equation, but that's equal to kilowatts per meter squared Kelvin. The temperature at the surface of the box is 300 Kelvin, and the temperature of the air is 293 Kelvin. And the magnitude of, I'm going to write this as an absolute value. The absolute value of the work done as input, that work W1, is 60 watts. And we want to know first, what's the rate of energy transfer by heat? And second, what's the power delivered through the output shaft? If we were doing something like this in like a dynamics class, we wouldn't have any measurements having to do with the temperatures. And if you knew the size of these gears or whatever, you could go through all these calculations, and what you would find is that even though this is a smaller gear, say, because of the different rate at which they're spinning, the work output would be exactly the same as the work input. Okay, yeah.
So does W1 and W2, they stand for work?
Yeah, they stand for work, and the total work, like W in our equation, is the sum of those two. Oh, yes, thank you. So this, yeah, so this is the rate of, yes. Yeah, thank you, that's important. So we're going to use that differential form of this equation. Okay, what all I was saying was, if this was a dynamics class, we don't have any use for this temperature stuff. And so if all you're dealing with is pure mechanical energy, then you have the same work here as here. But if you do know some things about the temperature, we're going to see that obviously this has to be lower than this. And we can figure out by the stuff that we know about the heat loss, how much energy is lost through friction. I guess it's all friction. Okay, so this is the input work. What's the rate of energy transfer by heat? So this is a convection problem. So the absolute value of Q dot is equal to H, that's 0.171. And we have some stuff in kilowatts and stuff, so we have to be a little careful with that. But, oh yeah, this one's in kilowatts. So that's 0.171 times 10 to the third. And then that's multiplied, I'm just putting everything in SI units. That's multiplied by 1 meter squared. And then that's multiplied by of the box minus the temperature of the air. So that's 300 minus 293. And I think now that I think about this, well, let's figure out what this is, and then I'll see if I have to change anything. Can someone multiply that? Times 10 to the third. Nine, 7 times 10 to the third watts. Okay, so for this to make sense, we have to change this value. This is supposed to be kilowatts. So W1 dot has to be 60 kilowatts. Well, this is just a mechanical box, so obviously it's not going to be gaining energy through heat. It's going to be losing energy through heat that's related to friction and stuff. But let's think about it just in terms of what we know about the signs of this equation. So remember, the equation said this is the heat that's emitted, right? And so we have a positive value of the heat that's emitted. This is a better way to write this. Let's get those out of here and just write it as E for emitted. Our system is going to be the box. So is Q dot positive or negative? So our system is the box. The box is emitting energy. So is Q dot positive or negative? Negative, yeah. Because positive Q means heat is coming, energy is coming into the system through heat. So Q dot is equal to negative 1.197 times 10 to the third watts. This negative means energy is leaving the box. So that's the answer to A. And then for part B, now we're going to have to put everything together. We're trying to figure out power delivered through the output shaft. And we have, so we know that dEdt is equal to Q dot minus W dot. dEdt, we can break that up into the time derivative of the kinetic energy plus the time derivative of the potential energy plus the time derivative of the internal energy. Those have to be equal to Q dot minus the quantity W1 dot plus W2 dot. And now all of these go away because this is steady state. Bless you. So if you have a steady state process, anything that's a property has no time derivative. It's constant in time. And so now we have that 0 is equal to Q dot minus W1 dot minus W2 dot. We just calculated Q dot was equal to negative 1.197 times 10 to the third watts. W1, the magnitude of W1 is 60 kilowatts, 60 times 10 to the third watts. So that W1 is energy that's being added to the box through work. So is W1 positive or negative? Any other? Yes. That's a little, it's always hilarious. And there's only two options. Okay, so remember the sign convention for work work is positive if your system is doing work on the surroundings, and it's negative if the surroundings are doing work on your system. So that shaft is doing work on the gearbox, and so that has to be negative. So we have negative 1.197 times 10 to the third minus negative 60 times 10 to the third minus W2. And so W2, this is W2 dot. So W2 dot is equal to 60 times 10 to the third minus 1.197 times 10 to the third. And so W2 dot is equal to 58.803 times 10 to the third watts. And does it make sense that, so that's the work that's done by the that second shaft. Does it make sense that that's positive? Yeah, because so the surroundings do work on the first one to make the gears rotate, and then that second gear does work on the surroundings. So it comes in as negative and leaves as positive. That's right, from friction, and the way we know how much energy is being lost through friction is from using those temperature differences in the heat equation for convection. And then just a lot of thinking about the signs. Yep. Mm-hmm. So yeah, it comes from, right, it comes from this. So there are going to be a lot of times where these things are going to be broken up. This Q dot is the sum of all the individual Q dots, and this W is the sum of all the individual W dots. You just add those in. Exactly. Yep. Exactly. Yep. Any other questions about that one?
On the steady state, and just for clarification, said that time derivative of properties go to zero.
If it's steady state, yeah. So steady state means that if you look at the thing at any instant, the thing is the same. So all its properties are the same, and that means they can't change in time.
And then brought back in. Would that still be a steady state system?
So if the oil is going out and in, we haven't talked about this yet, but then what you have is your system is not the same material particles through time. You know what I mean? Because heat is leaving as the oil goes from here. And so for that, we talked about this like on the first day that we're going to have two types of things. Closed systems, where over time you're looking at exactly the same material particles. And then control volume, an open system, they call it a control volume approach. And then you're looking at the same volume the whole time, but materials are traveling in and out, and you have to account for those. And we'll talk about how to do that stuff pretty soon. It's definitely easier. The problems are always going to be easier if you're looking at a confined set of particles. Any other questions about that one?
I guess one question that comes to mind, almost the same question, but is so is a closed system a necessary condition for a steady state system?
I don't know. Energy. I don't think so, because I mean, you could have, if you're looking at this, so if your system is this volume, all you care about is the properties of the volume, and so if the properties inside that volume aren't changing while stuff goes out this way and comes in this way, you would still call that steady state. Yeah. Any other questions? Okay, well, let's stop there. And on Thursday, I will do one where we don't have a steady state. We have a transient system, and we just know how one of those properties is changing with time as a function of time. And the quiz is on Thursday.